Okay, we're going to look at formal differentiation, the first differentiation rule that we'll use, the main one that we'll use in year 12, and you'll get more of them in year 13 when you do more calculus, if you do more calculus. So at this point, we've been finding the gradients of a tangent and a point on a curve. And what we realize that what we're doing when we do that is we're basically, at a point. If we have a point and we draw a tangent line to that, we basically are finding, if we find the gradient of that tangent, we're finding basically the instantaneous rate of change at that point, which is differentiation by virtue. We're doing calculus. So there is a better way of doing this than always having to find, draw a tangent to your polynomial, if you will, and that's using a rule. So the rule that we're going to use is called the product rule. When we try to find the gradient of a tangent and a point on a curve, we are finding instantaneous rate of change along that curve. Basically what we're doing is called differentiation, right? So that's like the verb, differentiation. We're differentiating. But we're not doing it formally. So instead of having to always draw a tangent and estimating the gradient of that tangent to get the instantaneous change, we use a rule, which is a lot more efficient, and it allows us to do a lot more things. There are several rules, but in year 12 we use the power rule, sorry, not the product rule, power rule for differentiation. So just sort of the vocabulary around this, differentiation is a verb. It is the process of finding the derivative. And another word for the derivative is the gradient function of a graph. When you're finding the gradient of a tangent on a curve, you're basically finding the gradient function. What is the gradient at that particular point means what is the instantaneous rate of change. Finding a derivative is a pattern that is used to determine the gradient of a curve at a given point. Instead of finding the gradient at a point each time, we differentiate. We use a rule to find the gradient at that point, okay? So there's a lot of vocabulary you've got to get used to using. Differentiation, which is a verb. You're basically finding the derivative or gradient function along a curve of a graph. And the power rule allows us to quickly find the equation of the gradient function. We use this then to find the instantaneous rate of change at a point. So, for example, if we take these three instances, we've already done this with our calculator. We put y is equal to 2x squared to our calculator, and we find what the gradient of the tangent is when x is 1, and we found the gradient of the tangent is 4. If we were to do that same exact thing for x is 2, we would find the gradient is 8. And if you don't believe me, you can check your calculator, and you can work it out with your calculator if you want. So I've got 2x squared, I draw it. I want to delete that, can I clear it? Yeah, if I want to draw a sketch of tangent at x is 2, I get a gradient of 8. The tangent, the gradient is 8, right? And then we do again for 2x squared at x is 3, the gradient is 12. Now you should start to see a pattern. 4, 8, 12, 2x squared, we put in a 1, 2x squared, we put in a 2, 2x squared, we put in a 3. Basically, you should start to see that what we're doing here, if I took a look at this, let's take a look at this one. Right, what I'm doing here is what's happening with the pattern is I'm going 2 times the exponent times the x, which is 3. 2 times the exponent, which is 4, times the x2, which is 8, and so on. So basically what you're doing is y is equal to 2x squared becomes 2 times 2, basically 2 times the exponent, times x, but x with an exponent minus 1. You're taking 1 off the exponent each time. So if you work it out, 2x squared at x is 2, we know the gradient is 8. So basically what we're doing here, what the rule is, we're taking the 2, we're timesing it by the exponent, which in this case is 2. So 2 times 2 times x, whatever x is, right? But we're taking 1 off the exponent. So in essence, what we're doing is we're going 2 times the exponent, and then x, whatever x is, if x is 2, doing that again, but we're doing it with 1 less than the exponent. So the exponent is 2, then it's 2 minus 1. So we're going 2 times 2 times, and then whatever this is, 2 to the exponent, 2 minus 1, which is just 2. Again, that's just 1 up there. So 2 times 2 times 2, which is 8. That's the pattern, right? You're taking 2 times the exponent, so you're bringing down the exponent, you're multiplying it by the number in front. So 2 times 2 in this case, times x, but it's not x squared, it's going to be whatever x is with, and 1 less. You're taking 1 off the exponent. So it's going to be 2 times 2 to the x to the 1. And in our case, it's 2 times 2 times 2 to the x minus 1, to the exponent minus 1. Okay? So it's a little bit confusing, but if you want to go back over that and watch that again, I'm going to do a little bit more of it right here. Okay? So don't panic. So here's what we're doing. The gradient of the tangent to a curve is called a derivative. Okay, that's a derivative. And one of the ways that we write the derivative is we use this kind of notation here, dy over dx. So if we use y is equal to 2x squared, right? The derivative of that is written as dy over dx, and then we use the power rule to write the derivative, okay? And the derivative is the rule that I just tried to explain. We differentiate functions to find the derivative. When we differentiate a function, we are obtaining the general rule for the gradient of a tangent at that function. So we have y equals, we write notation of dy over dx. If we have f of x, function notation, if we use function notation, we basically put a little prime mark on the f. So we use f prime x. That represents the gradient function or the derivative. Dy over dx represents the gradient function or the derivative. So you can use derivative, oh God, I can't possibly, derivative, just gonna type it, derivative, right? Derivative, gradient function, they mean the exact same thing, but the notation for it is dy over dx if we're referencing y equals, and it's f prime x if we're referencing f of x for the original equation. So the rule. Let's try this rule thing again, the product rule or power rule, if you will. What do you do first? You multiply the coefficient. The coefficient is a number out in front of the x, in this case a, by the exponent. So a times b. So a times the exponent, a times b. That's the first step. Second step, subtract 1 from the exponent. So in this case, it's b minus 1. If there are several terms, differentiate each separately. So that's it. That's all you're doing. So let's just see how this works, right? So y is equal to ax to the exponent b. Is the differentiation of that is dy over dx is equal to a times b times x to the b minus 1. So you bring down the exponent and you multiply that by the coefficient in front, a times b times x, to 1 less than the exponent, b minus 1. So let's see what that looks like when we do it here. So I'm going to go dy, because it's a y equals, so it's going to be dy over dx is equal to, worry about the capitalization of this. And then what's the rule? Well, there's a 1 in front of that x. There's actually a, in this case, is just 1. So you're going to be going 1 times 3, so that's a times b times x with an exponent of 3 minus 1. 1 less than the exponent, right? So that basically becomes dy over dx equals 3x with the exponent 2. So there's the derivative of y is equal to x3 becomes 3x squared. That's the rule. So if we want to find the gradient at any point along the curve of x is cubed, x cubed. So if we draw the graph x cubed, right, which is just a positive cubic, and then we want to find the instantaneous rate of change at any point along that curve, any point at all, anywhere along that curve, we will use this formula to find the gradient function or the gradient of any tangent along that point. So whatever x is, it could be -3, it could be 2, it could be 1, whatever point you're dealing with along that curve, wherever you're dealing with it, you would use that formula to find the instantaneous rate of change at that point. Do the same for this one. Now we've got f of x, so we use f prime x, and we differentiate, right? So it's going to be 8, so this has a 1 on it, so b is 1, the exponent is 1, so it's simply 2 times 1, a times b, times, so that's that, and then x, and it's going to be minus that, so it's x0. So guess what, x0 goes away. So in this case, f prime x is simply 2, it's a constant. The x just drops off because it's going to, if it's 1 there and it's 1 minus 1, then the rule is just, it's a constant. This is a straight line, and the derivative of this is 2. So that just means that it's a straight line of 2x. That just means that the gradient at any point along that line is 2. The gradient is 2. You see the relationship? Y is equal to 5 is again the same idea, dy over dx. But we've got a problem, Houston, because we've got no variable at all. Nothing here. We've got nothing here. So what could we put there to represent a variable? What could we do? What could we do? That? Can we do that? Think about that. Y is 5. What is the derivative of y is 5? So if we use the principle, we've got no variable. So how could we do that one? We've got no variable. It's another way of not having any variable. It's x to the 0. Right? It's x to the 0. So what happens if we have x to the 0? That's just 1. And if we minus 1 from that, what do we get? We don't get anything. We get the big fat freaking 0. We get 0. We get a 0. We get 0. We get 0. There is no number here, because if we have a 0 there, 5 times 0 is 0. It doesn't matter what the exponent becomes up here. If we take away 1, it doesn't matter, because this is a big fat 0 on the top. X to the 0. That's another way of writing when you don't have anything there. X to the 0. So it's 0 times 5. So the answer is 0. Y is equal to 5. When you differentiate it, when you do the derivative, it's just 0. Keep that in mind. And then this one, again, it's going to be f prime x is equal to. Now, one of the things that you can do, what is a? What is a? What's the thing out in front, right? So what's a? Well, a is a half. So another way of writing this is this. Bring out, if you've got a fraction, bring it out in front. That's a, right? So then it's going to be a times b. So it's a half times 3. A half times 3. What's a half? Oh my God, what's a half times 3? Oh, 3 halves. So it's 3 over 2, x, 1 off the exponent, x squared. Could you do it as 1.5? Sure you could. But when you've got it over 2 or over 3, basically just think of that as a fraction, bring it out in front, and then it's just a times b. A is a half times 3 is 3 over 2, x squared. Now you might want to pause the video at this point and try, these are on the OneNote, see if you could do these. See if you can now figure out how to do this. So if you want to go to your OneNote and try these 3, differentiate these, okay? Pause. pause, go. Otherwise, I'm going to differentiate this as dy over dx is equal to, so I've got a 1 here, so it's going to be 5 times the 1, which is 5, and the x, it's just 1 minus 1, so it's 0. So it just, the x goes away, it drops off, and you get a constant here. When you have a linear function here, the derivative is a constant. 3x, sorry, so I'm going to move this up, 3x cubed, again dy over dx is equal to, and then it's going to be 3 times 3, a times b, which is 9x, 1 less x squared. There's the derivative. And this one is going to be, okay, it's f prime x is equal to, it's going to be 1/3 times 3, 1/3 a times b, which is just 1 x with 1 less x squared. That's it. So that's using the rule. That's coming up with a derivative. That's working through and showing the derivative of rule or formula for finding the gradient at a particular point on a curve. If you need to watch this video again, feel free.